Welcome everyone to another OCP tab called number 153. It's my pleasure to introduce Nikolaus. Nikolaus holds a master's degree in communication engineering with distinction from the Vienna University of Technology, also known as TU Wien. He went on to lead the ASIC design division at the university's Institute of Industrial Electronics, where he managed numerous research and industry projects focused on distributed systems and highly accurate fault-tolerant clock synchronization. In 2001, he co-founded Oregano Systems, a university spin-off transforming research results into commercial products suited for precision clock synchronization under the Sync 1588 brand. In 2019, Oregano Systems was acquired by Meinberg, a global provider of clock synchronization solution, and Nikolaus continued to contribute to the field as an active member of the IEEE 1588 Standardization Committee and the SMPTE 32NF Standard Group. And he's regularly delivering seminars on synchronization for both industry and academia. Please join me welcoming Nikolaus.
Thank you for the kind introduction. So, if it's okay, let's get started. Okay, what I want to give you a little bit of a background to is how to synchronize nodes with PTP in the nanosecond scale. I dubbed my presentation like precision versus practice. So I'm in the first part, I will try to highlight some of the more theoretical background ideas. And in the second part, which is, we believe, equally important, I will cover the pitfalls waiting for you when you actually really have to integrate that and put that into a product and try to evaluate whether that works as expected or not. Mike Sani Savcevic is working on the measurement system. He's actually his background is with the Metrology Institute, and sort of he's our guru in qualifying frequencies and phase measurements accurately with very high precision and reliability. Roland was one of our founding partners, and he worked in different areas, left Oregano many years ago and returned, so to say, to the fold, and is one of our very experienced FPGA designers working in that specific area of picosecond clock sync. So to start with, do we actually need sub-nanosecond, picosecond clock synchronization? I believe picosecond accuracy is no longer an esoteric requirement for the guys hunting or having hunted the Higgs boson, and they will find other bosons and other particles to hunt for. Just two applications which come to mind when we are looking into really single figures or 1 nanoseconds or 1 nanosecond, which, for example, is the whole wireless O-RAN field of application. They have seemingly stress-stringent requirements. The O-RAN overall error budget end-to-end is 1.5 microsecond. So, of course, it begs the question why we are talking about nanoseconds when the budget is microsecond. However, each device in larger network eats away from that budget, and the wireless channel, for example, claims some something like 250 nanoseconds of alignment error, which just a wireless channel requires. And if we look at one of their diagrams from one of the Oran specifications, you see the overall budget is plus minus 1500 nanoseconds. But if we look into more detail, then all of a sudden, as accurate as we possibly can get on a per device basis, that's sort of the winning way to do that. One other application or area of application is if we have really mission critical problems to solve, they would typically specify an absolute upper limit. The phase of any two nodes must never deviate from each other. So if that, for example, is 10 nanoseconds, then we have to allow for sufficient headroom to never ever even come close to that 10 nanoseconds. So if we are able to design something which is half or maybe one order of magnitude more accurate, then we are sort of really on the safe side. And one other data applications, of course, if the CPO clock needs to be synchronized to the PTP hardware clock in the NICs, using this as a reference, if we want to have very accurate clock synchronization using modern methods like PTM, then of course, the more stable that reference, that local reference is, the better I can synchronize my CPU clock to it. If it sort of oscillates all over the place, then of course that oscillation, regardless of how sophisticated your control loop is, will be amplified. One other applications emerge. One example which I find quite appealing is radio astronomy. That large-scale radar arrays, one of them is the ALMA, the Atacama Large Millimeter Array. I've added some links to that. They have a large number of this parabolic antennas, and if you can synchronize them very accurately, then effectively they operate as one huge parabolic antenna. That's a picture of that, and they deliberately chose that desert. It's I guess in South Peru, which is elevated like 4,000 to 5,000 meters above sea level, where you have hardly any pollution deteriorating your reception of your radio signals. So now let's look into the basics of nanosecond synchronization. The basic equation stays always the same. We establish a bidirectional time transfer, draw the timestamps T1 to T4, and the offset is a simple equation that will give us precise time. Second?
I think it was a hot mic. Go ahead.
Okay. That should give us precise time transfer. However, what are the limits we have to address? The timestamps are drawn with limited resolution. In typical FPGA implementation, you would have maybe a clock running at 250 megahertz or maybe higher, 500 megahertz. It's still limited to a couple of nanoseconds, several nanoseconds. The basic time resolution of that information is limited to 1 nanosecond. There is, you can add sub-nanoseconds via correction field. So there is sufficient headroom in the standard itself, but still sort of that's the basic limits we have to work with. And of course, the transmission time has to be, may neither be constant nor identical in both directions. And both of these shortcomings will deteriorate your synchronization accuracy. So, and your hardware clock, the PHC, the PTP hardware clock adjustment mechanism, may be too coarse because you want to speed up or slow down the rate of your clock, and that increment may be, the resolution of that increment may be too coarse to actually reach that level of accuracy we are striving for. And one other thing, data preprocessing may not be up to the task. So I will try to cover all of these topics in the next slides. So how to reach nanoseconds, even sub-nanosecond accuracies. First, of course, we have to increase the timestamp resolution. And secondly, we have to be able to adjust the rate of our hardware clock with a very high resolution and with high accuracy, i.e. high stability of the oscillator driving that clock. And what's also of importance is if we end up having synchronized all our clocks in our network to, let's say, our ideal green figure of 1 nanosecond, then how to use that very high precision in the end user application. Because on an application level, we as clock synchronization guys, we are happy that we have all the measurements done and that now all clocks are synchronized. So our job is done. The job for the application, actually, the engineers building the application on top of that highly accurate synchronization module starts right now, actually. And so we have to think about how to provide that high level of accuracy in a best possible way to the end user application. So let's look into how to measure phase differences between two signals in very high picosecond resolution. Typically, they would be implemented in modern FPGAs where we have system frequencies of up to 500 megahertz, which can be achieved with sufficient headroom and without actually squeezing everything out of the design system and the FPGA respectively. So, of course, it should be as technology independent as possible, feasible, assuming we have a dynamic range. Our clock, for example, runs at 250 megahertz. So our basic timestamps are quantized with 4 nanoseconds. So if we want to increase our timestamping capabilities, then we can actually limit our dynamic range for that additional circuitry to 4 nanoseconds because the higher dynamic range to actually grab the absolute time is handled by the PHC anyhow. So I will cover two methods we actually have implemented in several FPGA families, trying also to actually prove that they are to a high extent technology independent. We've implemented both in Altera and AMD FPGAs. And the basic thing is we want to, I will focus on two of these, which are able to measure single shot events. Sorry for the typo here. Single shot events, which is a time to digital converter and which are phase shifted parallel counters. When we want to measure offset of two phase locked frequency, we can use other implementations like the one used in the White Rabbit project, more or less exclusively referred to as digital dual mixer time difference. So let's look at the time to digital converter. We have two rising edges and we want to actually measure the phase difference very accurately between these two rising edges. So what we can implement in an FPGA is actually we would implement a delay chain like these. Sort of that's a chain of buffers we can instantiate, and each input of the first buffer and the output is attached to the D input of a simple flip-flop. And what we do now is one of these signals is routed to the clock input of these, and the second is routed to this chain of buffers. And if so that rising edge traverses buffer by buffer by buffer by buffer. And then all of a sudden, we have the rising edge of the second signal, which of course has to occur later than the rising edge of the first signal. And at that very moment, the status of output of all these buffers is latched in that row of flip-flops. And of course, afterwards, that the rising edge, the digital one, continues to traverse to that chain. What we have now is we have that information locked in a thermometer code, and we can actually read out that if we know the delay of one single buffer. These are a couple of measurements. What you see here is on the x-axis, it's actually the delay in the phase difference in picoseconds. And due to our measurement lab setup, we have only at that time distinct values we can measure. But important is the reproducibility, and you see the measurement phase error, and that phase error on the y-axis so is for a given delay, for example, of 1 nanosecond, 1000 picoseconds, we repeated that measurement many times, and we ended up in something. If you look, for example, at that one, if we ended up at plus minus 30 picosecond measurement uncertainty. So bottom line, that measurement principle is able to measure single shot phase differences with a very high resolution and repeatability. If we look towards accuracy, we have, of course, to consider that there is a calibration circuit required for that, because the delays are temperature dependent. We made temperature measurement, and typically these delays would vary over a senseful temperature range of maybe 40 degrees dynamic range would vary in more than 10-20%. So that's quite significant, and that would actually reduce the overall accuracy. So you need to add some kind of calibration using a well-known frequency, as, for example, we can use a reference frequency whose phase we know precisely, and we can measure the phase difference of the two of our unknown phase difference, and every other time we would measure a known phase difference. For example, rising edge of a known frequency versus the falling edge. And so we can continuously calibrate that. One other a principle to measure phase offset with a very high resolution is if we measure sort of the phase, or that we want to know the position of that rising edge, and we have a frequency, for example, our 250 megahertz, then our resolution, if that f is 250 megahertz, our resolution is 4 nanoseconds, 1 over f. So that's the maximum what we can get. So our result will be quantized in multiples of 4 nanoseconds. But one first approach is, rather than measuring only with the rising edge, we can actually double that and measure both with the rising and the falling edge. Then we double the resolution to 2 nanoseconds. And modern FPGAs allow you to actually use their internal PLLs where they output phase shifted signals. So you input that, for example, 250 megahertz, you feed that to a PLL, and then you can generate phase locked signals with a known offset of 45, 90, 135, and 180 degrees, for example. And then, of course, all of a sudden, your phase resolution will be far higher than your original 4 nanoseconds. The advantage of that principle compared to the time to digital converter, of course, it's far less temperature dependent. However, as routing delays have effect on that, and of course they as well are to a certain extent temperature dependent, we have to analyze the temperature dependency of such a circuit as well. For these circuits, digital simulation, timing analysis are very helpful tools. Again, we have implemented these circuits both in an Altera device. For basic tests, we use a RIA-10 device, and we use the Xilinx AMD UltraScale Plus. So yeah, that you can see the resolution is that. And if we run it, for example, at 500 megahertz, we end up with a 250 picosecond sample resolution, which is significantly below, of course, our initial 4 nanoseconds. Again, these are measurements of we wanted to analyze, again, the reproducibility of the measurement, and you see they are roughly in the same sort of, the error spread is roughly in the same range than with the TDC. So now, first task, let's say we have completed it. We are able to measure phase offset with a far higher resolution, and if our oscillator is stable enough, of course, with far higher accuracy than our original starting point of that 4 nanoseconds. So now we know the offset between our reference and the local device whose clock we want to adjust to our reference, to our PTP grandmaster. So one major factor we need to consider before going into detail how we do it, we need, and that is at least in my experience when I talk to customers of ours, that is a little bit overlooked, is if the more accurate you want to synchronize your clocks, the more stable oscillators you need. And we are looking at a short-term stability. As opposed, we effectively build a PLL. However, that's not really a PLL in the traditional sense. It is a device which tries to actually synchronize or two absolute time to add to time of day clocks with each other. So we have zero phase offset, and if we have zero phase offset or phase offset which remains in that magical one plus minus 1 nanosecond, of course the frequency will be also, the two frequencies will be identical. But as opposed to a standard, to a traditional PLL, we have far less information. A PLL a device will use sort of more or less every rising edges, the phase offset of two rising edges of input frequency and the one we want to generate. So we have to, and with specific circuitry, that phase offset is forced to zero. That's the basic idea. A lot of rising clock edges. In a PTP environment, we may have one message. That's bad design. Typically, we would have 16 messages, 32 messages per second. There is not more information we can use. So our timestamps, we draw timestamps in most applications, let's say 16 times per second. So, and even if we use each and every of these 4 timestamps to immediately adjust the clock, there are several ways to do that. We can adjust it with every sample we take, or we can sort of collect these samples, run some pre-filters, and adjust it even less frequently. But then what happens in between two adjustment cycles is unknown to us, because implicitly with all our control loops, we assume that the phase offset between two adjustment cycles is perfectly constant, which of course is not really the case. But the more stable the oscillator is during several seconds, the more accurate or that assumption is actually fulfilled. And typically, basically, when you use temperature control oscillators, you can get devices down to 0.1 ppm. And if you look at 0.1 ppm, that's sort of worst case condition. It's 100 nanoseconds per second off. So if that frequency really drifts during 1 second for 1.1 ppm, then your offset is off by 100 nanoseconds. So it's totally unusable for us. We cannot use TCXOs. OCXOs nowadays, they go down to 1 ppb. So, and that's where we want to go. Typically, you have variations over temperature, which is the main factor of frequency variations is temperature. So bottom line, without OCXOs, it's a lost battle. So typically your device would be set once during startup to account for a large offset. Subsequent adjustments should change only the rate to avoid jumps back and forth in time. And again, if our readjustment is once per second, then what resolution do we need? We have to account for nonlinear frequency variations as a function of time. They are maybe in a couple of seconds, they are somewhat linear, but they can be nonlinear as well. You cannot assume that with changing of temperature, you will have a linear frequency drift. We made a lot of measurements showing that that's unfortunately not the case. And if we want to have the offset remaining in plus minus 1 nanosecond, so maybe plus minus 2 nanoseconds, then our adjustment resolution has to be the resolution of the rate change we apply to actually account for a frequency variation has to be very low, like 0.0 pp, 0.01 ppb, for example, allowing us to really drift back and forth. So how to achieve that in network interface cards, in IP cores, in switches? You would have typically two methods to do that. You have some kind of digital way to adjust the rate, because depending on how the internal architecture of that PHC is actually built. But these are typically limited. They have limited resolution. The other way to do that is use digital tunable PLLs, which drive the PHC. There are a number of vendors offering devices capable of doing that. SiTime, these guys have recently acquired the Renesas timing division. Texas Instruments has devices. Skyworks has devices, and others. Just to give you some figures to work with, typically the phase jitter of these devices is between 50 and 200 femtosecond. So they are highly optimized PLL chips, and the frequency can be adjusted at a very, very high resolution. One of these devices, for example, can adjust it in 0.005 ppb increments. So we have a very high dynamic range and a very high resolution to actually play around and account for even small frequency changes via our control. And these are real-world measurements just to illustrate the frequency, the dependency frequency variations of different oscillators. The blue curve is a standard off-the-shelf TCXO, which is actually not too bad compared, works fine, but not really suitable for the purpose of having 1 nanosecond accuracies. A SiTime TCXO, for example, that's the red line, is far better. And if we look at the OCXO, we didn't account for sort of a frequency, initial frequency offset. So you see the frequency variation, for example, of that OCXO is at least 1, maybe 2 orders of magnitude better or lower than the even a very good TCXO, and a standard TCXO is maybe 2 or 3 orders of magnitude worse in the frequency variation. And that's just that's at ambient temperature in our lab with sort of normal temperature changes due to maybe HVAC, things like that. It's not running a complete temperature cycle. I would assume we have made some measurements. The temperature varies with less than ±5 or ±5 degrees temperature variation is that. And what you on top see maybe is also, for example, for the TCXO, you may see also some frequency variation due to the inner work caused by the inner workings of the device, which are which have a very, you would see them in the OCXO as well, but they are far less prominent than in the TCXO. Okay, so let's now we have our timestamps, we have our stable oscillator. Now let's look at how to process the timestamps. Typically, when we receive that, we receive timestamps in 48-bit seconds, and 32-bit nanoseconds. That's sort of the native PTP time format. And we have, as I mentioned earlier, a correction field where we have additional, we have the opportunity to actually get more info, put more information, exchange more information. That's a 64-bit scaled nanoseconds, which is nanoseconds divided by 2 to the power of 16. So we have sufficient resolution, and we have what we have to consider. We have a huge dynamic range to cover. So that's 80 bits and maybe some fractional. So we do need data preprocessing to actually handle, for example, outliers, which would kill any high accuracy information, because the odd timestamp can be drawn incorrectly by whatever device is in the chain, or we have maybe some additional errors in the digital circuit, transients in the digital circuitry. Every now and then you may have excessively wrong timestamp to handle. Typically with nonlinear filters, you run some statistics, and if everything is settled after maybe a couple of minutes, then you know the range of the error range. You can calculate mean values, standard deviation, stuff like that. And if you encounter one of these excessively wrong timestamps, you simply discard it. And on top of that, you would add some low-pass filters to reduce the noise even further, and to handle maybe additional quantization errors you still have, like decimation filters, IRR, FIR, moving average, whatever is working best for the specific application. If we look into the internal data representation, if you run it with standard IEEE double, your mantissa is 53 bits. If you run it with 64-bit integer, that would be sort of the internal data representation of everything. Then you need to work with that extended dynamic range anyhow, because we have more than 64 bits. But if we actually just look at the nanoseconds and skip the MSBs, a number like 16 MSBs of the seconds, which typically will not change, then we could work, and a lot of people work, a lot of implementations work with 64-bit integer. However, if the more extensive the pre-processing becomes, the more prone it is to introducing quantization error. I don't say that it won't work, but it requires typically normalizations for every filter, and adds a level of complexity to actually building that. A lot of people build that. It's by no means impossible, but you may, if we run these control loops and these filters, sort of that basic normalization is rather straightforward to implement. However, if we are really tackling some nanoseconds, then we may every now and then stumble over that. A modern approach, which we are looking into now and where we have built first implementation, is using 128-bit integer. It simplifies the filter design, and first tests actually show that the computing penalties are more or less negligible in modern CPUs, because we do not run that. The amount of processing we do is limited anyhow, because we have like 16 message exchanges. These are, and with that we run some filters and maybe linear, non-linear filters, but the amount of data processing is limited per second, because we have typically to readjust it once every second. So there is not really much work to do for a modern CPU. I just show you an example. We run it, that's first implementation of our 128 internal dynamic range at a message rate of 16 per second, a back-to-back connection with a 250 megahertz running our PHC. And there you see that's the raw offset. As we have already decimated it, we have a quantization in 1 nanosecond. And if we actually apply all the filters and all the and feed that into the control loop, we end up in something like plus minus 1.5 nanoseconds. And that's actually what you see here is to achieve that, we need to adjust the frequency of the PLL driving that PHC at a very high resolution. That's ppb. Keep in mind on the that's ppb. So, and that sort of justifies what I mentioned earlier, that we need a very high resolution. Sort of the dynamic in the steady state, the dynamic range, or the range we are looking at, is plus minus 1 ppb, adjusting the frequency. And just to give you an example, that's a 64-bit internal dynamic range, is still in more or less the same range. But what you can see here is some low frequency oscillations, rather constant frequency. We actually started to analyze that, and we are pretty sure that is sort of the effect of some quantization errors, which actually add up and causing that phenomenon. Okay, I mentioned that we adjust the frequency of the local clock using only the time information provided to us by via the PTP messages. Would synchronous Ethernet, a lot of people actually deploy it and use it, would that help us out? Well, it more or less transforms Ethernet into a hierarchical frequency distribution network. To actually make use of that, we have to have hardware to support frequency transfer. We need rather accurate local oscillators as per the standard, the underlying standard, somewhere in the ppm range. And we would definitely, to actually make use of that sync frequency for clock synchronization, we would need local PLLs to clean up the input frequency. And then we would need a protocol stack to actually establish that hierarchy. What we have to keep in mind is that the ESMC, that Ethernet synchronization message channel, where it's linked between, it's link local, and it exchange frequency information exclusively only between two adjacent nodes. It's not something like a best master, best frequency selection algorithm compared to the best master clock algorithm in PTP. It's not network wide. You cannot select, rely on a standard. Any type of implementation and configuration is therefore user specific, application specific. It can be used to improve PTP synchronization accuracies because all devices benefit from a single base frequency, and that was a measurement we made some time ago, where you see here we switched, that's output of a Calnex device, where we actually compared the phase offset. That's really measurement of 1 pps, offset of 1 pps, the dynamic time error. And you see here that these are the areas where I switched on SyncE and then I switched off, and sort of it's rather obvious that the synchronization accuracy will improve with synchronous Ethernet. So now, major part is also how to actually measure synchronous sub-nanosecond reliably. What we want to do is we want to compare two 1 pps signals of devices with each other. How to best do that? Best implementation is a counter timer, counter interval timer. The phase resolution of that device, typically modern devices have a phase resolution in the area of 10, maybe 20 picoseconds, which is a decent value and not that expensive a device to actually acquire. On top, I will show you why we strongly recommend to at least to calibrate your measurement to use a high bandwidth digital scope. Typically, we have that's these numbers are of what we use drawn from what we have currently in our lab available. And please keep in mind the scope alone is just a half the solution. You need high bandwidth active probes. And you need a very stable external reference. Typically 10 megahertz, every device is able to run off an external megabench to supply all devices. It could be a rubidium, it could be a high-grade OCXO from, for example, a PTP Grandmaster, which is disciplined to GNSS. What we want to measure is the time error, which is the constant time error, and the dynamic time error. So what we need to do is to actually measure sub-nanoseconds. We have to calibrate all devices and components, cables, probes. We have to analyze different channels of our measurement units, be it the counter timer, be it the DSO. If the channels have same latency, that's easy. That can be implemented by just switching the channels or having a well-calibrated measurement test fixtures, which actually splits the signal into onto the two channels where we actually know the delays of that splitter on both channels. What I strongly recommend, use active differential probes and define your reference points. That is a typical application. One counter timer we are using with an external frequency. The cable delays, of course, are critical, but the time is generated here and synchronized. That's the reference in the FPGA. However, we have only access to that signal here, and that delay has to be known and accounted for. Typically, vendors of your specific equipment will provide you with these information. You can actually extract them with tools, with the printed circuit board tools on delay. You can measure them on traces on the printed circuit board, and within the FPGA, you will get information from the respective FPGA design system. I wanted to just highlight why differential probes are rather interesting. That is the spread over several measurements using a differential probes or two active probes. And you see, you need to actually really invest also in your measurement equipment. So why did I focus or mention the digital scope? That the counter timer, which is a perfect tool because you can get along, you can configure that and you can grab the data for a really long-term measurements. We run these typically over many days to actually also get information about the long-term stability. But when you actually want to measure the offset between these two signals, you have to define the trigger point in that. And then when you define the trigger point, you have a certain uncertainty. And depending on the signal and the trigger point, that uncertainty can be either larger or smaller. What we actually want to do, we want to measure that time interval. But what the counter timer does, it actually has an internal trigger. When the signal reaches the rising edge, reaches a certain level, then the measurement is started and stopped respectively. So to actually analyze how that device will actually treat the signals, you need to know how these signals look like when they enter your counter timer. That's the reason why we actually have to measure them with an with something like a digital scope, and not rely on let's do auto trigger or things like that. Then you may end up with very inaccurate or unreliable results. So that's just to give you a little background. That's our counter timer. There we used two active probes, single-ended here, and there we have our digital scope. And that's also important. All the cables have introduce latencies, introduce delays, and these delay, what we did with certain cables, where we actually we measured all our cables in our lab, but certain cables, and that's the one with the red text, we actually went to a metrology lab and asked them to actually qualify them with their measurement equipment, so we know see, you can see that cable has 10 nanoseconds plus minus 50 picoseconds. And that is provided by a metrology lab. Okay, so now we have synchronized it, we have measured it. Now, last step is how to actually make best use of our very accurate time. What we can do is, and that's what customers typically, that's the most common application and requirements customers would ask from us, is we can sample external events with that very high resolution. We actually use that same principle in a two-step procedure. We grab the timestamps from the PHC with a resolution of 1 over the PHC frequency. In our implementation, that would be maybe 2 or 4 nanoseconds, and then we measure the phase offset of the event to the timestamp using one of the methods I described previously. And then we have a very accurate event measurement, and we can do it the other way around. We can generate trigger signals at a given point in time, again with a two-step procedure. However, that's far more that can be more complicated, because the inherent resolution again is 1 over the PHC frequency, but we can shift that output signal if we would require something like not multiples of 4 nanoseconds, but we need 3.5 nanoseconds. Then we would use additional time to time to digital converters, sort of the other way around, and actually phase shift that signal. It's the same principle, but of course the circuit looks a little bit differently. And the third sort of way to make use is you can use the time typically internally within the FPGA, and there is a big caveat to consider. All that what we talked about was within the clock domain of that, be it sync-E or not, in that PHC clock domain. So everything is running off that 250 megahertz of that frequency, which we are also currently adjusting, things like that. And if the system requires other circuitry to run in a different time domain, in a different frequency domain, running off a different oscillator, different frequency, then we have, by definition, a clock domain crossing between the PHC frequency and the other system frequency. And that, again, causes inherent quantization errors that may also cause some other effects where we have to be careful to synchronize signals from one domain to the other domain. So even if we have something in sub nanosecond, we may lose some of this high precision if we move that information from one clock domain to the other. However, be aware of reference planes for all signals. So let's conclude. More and more applications we see require nanosecond or sub-nanosecond clock synchronization. It's tricky but doable. The performance of all devices has to be considered. The interface to the user application may deteriorate the overall accuracy. Verification is not straightforward. We have to look into calibrate all our measurement equipment to actually be really sure what we actually have achieved. There are further readings. There is a number of very interesting blog entries on working on the whole measurement, GNSS and UTC, and there is more to come on that Meinberg blog. Thank you.
Thank you very much, Nikolaus, for this informative presentation. Let's go for some questions. So, maybe we can go with David. David had, let's see. Bashar had the first question. Bashar, do you want to ask a question?
Yeah, hi, thanks. Sorry, I have to actually step away, so I'll make it very quick. My question is really in terms of one of the applications you mentioned is CPU synchronization to PTP for data center applications. Is the context of your reference to CPU-based sync only with respect to Intel TCC capable devices?
Yeah.
Okay.
Otherwise, it's not. Yeah.
Right. So my concern is that most data centers today are not deployed with TCC-enabled capabilities.
I know.
Okay. So
we are in the transitional period.
Right.
We worked with sort of standard devices, and if you actually squeeze out each and every part of that, you would end up in well below 1 microsecond, but in several hundred nanoseconds. But that's more or less it. Not you lose 1 to 2 orders of magnitude. Orders of magnitude. No way around.
Yeah, no, I understand, and that's what my concern was. Okay, very good, understood. Thanks.
Yeah. One thing I want to add is Intel CPUs have the TCC, or PTM, and the other non-Intel CPUs are also catching up. So that's all I can say. Okay, David, do you want to add anything to your question or something?
Oh yeah, I had a few, but one just following up on that. With PTM, as I was just talking about, are you saying you see 2 orders of magnitude or 1 order of magnitude difference? My understanding was a ballpark about 10 nanos.
PTM versus non-PTM, at least 2 orders of magnitude, maybe more. That was.
And has anyone analyzed that if you're doing specifically dual socket and you remove the kernel from one of the other sockets to really isolate everything, and then pin interrupts and all the normal sort of ultra-deterministic tricks?
There are a lot of tricks. We worked on for that several years ago. We didn't use the most modern techniques with which modern CPUs provide. But one important point is you can get rid of a lot of inaccuracies, like if you have preemptive, if your PCI Express access is preempted, things like that, you can read it many times, do some math, things like that.
Exactly.
But what you end up with is a basic assumption, which is dangerous. You assume that the round trip delay is identical in both directions, and you divide it by 2. That is something which is nobody really knows for sure, and you cannot measure unless you have PTM. You cannot measure the actual. You only measure the round trip. You cannot measure sort of one way. which you would need.
Is that something though that Intel would be able to do?
Yeah, with the PTM you can do it, but
no. I mean, could Intel, given that they have the schematics
no,
of
I
the
don't think
chips,
so.
could they actually do clock level simulations to know if it's symmetric or not?
I don't think so.
Interesting.
If
Okay.
they do it, I'm quite sure they keep it to themselves.
No, so I was in consultation with Intel on this specific problem when we started discussing VNF capabilities. This is something they were not able to achieve with their legacy silicon.
Yeah.
Gotcha. And similar, you're talking about using oven-controlled crystal oscillators. Have you tried using rubidium or even some of the more advanced ones now, like inflection as the hydrogen maser you can finally put in a rack?
Best what we have is we have a decent rubidium in our lab, and we have double oven OCXO, which actually we will combine these two. That's what's currently in the making, to have long-term and short-term stability, combining these two frequency references, providing that, because both have limits and pros and cons. Investing into masers, it's currently not on the table.
Hi, this is Paul. I just put a document in the chat, so I'd like to get some comments on this. We are submitting this to a referee journal, but it's up on the archive right now, or at least it will be by Thursday. So I'm addressing this question about whether engineered simultaneity, particularly in David's world, actually is saying something meaningful with synchronized clocks. So I would appreciate some comments on that if anyone would like to read it. You will need to download it before the session closes.
All right. Frank?
Thanks. Yeah, so I'm looking at the high accuracy synchronization less from a OCP angle, which is all about, data center scale, big, expensive equipment. I'm from the automotive branch.
Yeah.
So with us, it's always, cost sensitive and so on. And typically in the car, the synchronization accuracy requirements don't go significantly below a couple of microseconds. However, there are use cases emerging where it would be interesting to get to the, let's say, 2-digit picosecond range. Now, I'm wondering, what do you think, how feasible it is to do that in a cost-sensitive environment with, let's say, few nodes, like one switch fanning out to, let's say, 4 nodes, FPGA-based, maybe SyncE for automotive is there already. They can do it. The question is that the extra gear that you need per node, the PLLs and the FPGAs,
you would
you think
need
you could get there?
Yeah, you would need FPGAs, you would need PLLs in each and every node. You have one very nice advantage in the car, that's the cable length, which is limited because cars are small compared to a data center. That's the good news. The really bad news is the temperature range in a car, which is minus whatever to plus whatever, depending where you live as a device in the car. And if we have to cover like 100 degrees temperature range, things will get tricky. I'm not implying that's impossible, but that's in my what we have measured and looked at. That's, I guess, the most critical thing to consider. Typically, you would need to measure the temperature, account for it, and have some calibration stuff, things like that. Temperature, I believe, is your worst enemy for picoseconds in the car.
Okay. Thank you.
Sure. But I don't want to dissuade you. It would be a cool project.
If you're interested, let me know. I could put students on it. We have all the gear. So, a question following up on the shorter distance, especially. Have you compared? Because this is something I'm planning on doing, but I'm curious the results of an ideal if you're doing something like PDP versus just doing coax directly into the NICs and how those compare with the pulse per second.
We made some measurements, but that is sort of using a 1 PPS coax in the NIC, but still, if you want to compare these, you need to have coax plus 10 megahertz to actually have comparable starting points, and then you have to actually it's quite a lot of work because you have to measure out of band your cable delays, which provide PTP helps you here significantly. And then sort of that, by the way, was one of the reasons why the CERN guys started the whole work, because their timing system, like 20 years ago, they had to calibrate each and every cable.
No, for longer distances, I can see that, but I'm talking strictly if you're just doing like 3 feet, let's say.
But still, you need to know it. 3 feet could help you, but you may have, on a per cable basis, you may sort of grab a couple of nanoseconds here and there.
Okay. I was checking some of the math depending on the different coax types, and it looked like it was, I think, the worst case were in the double-digit picoseconds. But I was just curious, have you run the experiment where you don't also have the 10 megahertz, and so it's just based on a pulse per second to then see what kind of performance you can get?
If you do it just on the pulse per second, then synchronizing that pulse per second, measuring that is rather critical. We made some similar measurements, but not in the sub-nanosecond measurements. So what we typically have when we attach our cards to a GNSS receiver, we end up in 5 to 10 nanoseconds, which is reasonable enough, but not in that level using 1 PPS.
Gotcha. Okay, thank you. I'll follow up too. This was a phenomenal presentation, and it was, no pun intended, very well timed. So this will help me. It saves me a lecture. I'm just going to point students to the recording. So thank you.
If you need any more information on that, just reach out to me, and we can check what we have on the data.
Yeah, and it'd be great to collaborate. So one other use case where this is extremely important is in financial services.
Yep.
So they're basically trying to capture market data so that you can then phase shift it as a function of the speed of light of when would certain Ethernet frames, could you get that data to every other data center on Earth? And there they at least have the time stamping ability of double-digit picoseconds. You look like some of the Arista gear from the Metamico acquisition. So that's where this was phenomenal. So it was great to see.
Mm-hmm.
All right, Jose. Jose still here? All right, I think he's not here. Anyone else? Anurag, you have a question or something?
No, I was wondering, is this comparable to the White Rabbit section? Because David was touching a little bit on that.
Well, White Rabbit drives it even further. We have been we are working on a White Rabbit solution as well. White Rabbit addresses a lot of other issues in networks. And so if you want to deploy a White Rabbit node, then you can only deploy it in a White Rabbit network. You need far more. You need additional protocols. You need message exchanges, things like that. It's sort of on top. What I wanted to focus here is how far can you possibly get without switching to White Rabbit?
Okay, on PTP alone. Okay, yeah, understood.
On plain vanilla PTP, so to say.
Yeah. Yeah. So in that case, as David said, what we usually do is we try to do NTP plus 1 PPS to get as much as closer.
Mm-hmm.
Also related to that, I was just curious, has anyone tried again for that in a rack case of instead of using actual switches that are PDP aware, just use a passive tap on a single output with known cable lengths and just wire it up to all the machines? And then just have a very high rate of continuously messaging.
We didn't do that.
Okay.
No.
It's on my to-do list too. I was just curious because I think it could be an interesting one and lower cost. Then you don't need the switch.
If you can share something, I would be really interested in that.
Okay, we have the setup, so it makes sense if you would like to collaborate. I'm happy to. It's a good experience for the students. So and you definitely know what you're doing. So this is phenomenal.
Yeah.
Tamaj, anything you want to add?
I guess the one we always have to ask at the end is, have you started looking at optical yet? With the sub-femtosecond syncing and
Yeah.
All right. No more questions?
Just one question.
Go ahead.
Hi.
Do you think, hi, Nikolaus. Do you think that we need sub-nanosecond timestamps, for example, in Linux? Because currently the API just sends you a timestamp in a nanosecond resolution.
Yes, it would be helpful.
yeah, especially if you just look at the bit rates and what they're doing right now with the Ethernet for AI. If you're at 800 gig, 1.6 terabit, these things actually really start to matter to the point of can you figure out the ordering of events in some cases?
Yes, precisely.
So for Linux, the D-message, the granularity is microsecond, single digit microsecond. And yeah, I don't know if going further, it really depends on the granularity of kernel running things. Otherwise, timestamps from external events, they can go whatever you want. They're numbers that they tie to something that happens externally. So.
But I mean, I thought it was configurable though. If there is an option you can run, I think it's on TCP dump of whether it's microsecond only or nanosecond. Presumably they can
for the kernel,
that
yeah. But the execution of events is like, I mean, you're not single CPU cycle. I mean, of course, you can have also, let's say, a physical error like cause, let's say, for example, a PCIe failure that can be timestamped to higher granularity. But then as it gets detected by the kernel, it's within the like a single digit microsecond or 500 nanosecond.
Gotcha.
Yeah.
It's like you stab the system, but it takes for the nerves of it 500 nanosecond. It's very
You mean
interesting.
that,
yeah.
Do you mean that it has an interrupt latency, like something like an interrupt latency? You need time to realize that something happens.
Yes, yes, yes. Yeah. It's like until it finds out the pain, you know.
That's why we busy pull and bypass the kernel.
No, I know this because I work with systems that with these multi GPU things, like the DGX H100, where you pull the sled, all of a sudden you kill all the PCIe devices, and then we kept doing this over and over to see like how it reacts, and every time, I mean, all GPUs were getting pulled, but I mean that's a very expensive toying around because the thing is like $200,000-$300,000. But that was like something was part of like, you know, readiness. And then every time like the order of like the GPUs going down was changing because it was an aliasing, and it was like getting like rounded to 1 microsecond. I mean, yeah, definitely you can probably patch that in the kernel or something, but I don't think the kernel has enough snappiness to get anything find the difference between those. Yeah. Anyways, so if no more questions, we'll see everyone in 2 weeks by a presentation from Kiel Beek, also a alumni from TU Wien, about frequency ratio of the thorium-229 nuclear isometric transition, basically for the nuclear clock. All right? We'll see everyone in 2 weeks. Bye, everyone.
Okay, thank you.
Bye.